Hi there, this is Ayush from Master Mechanical Design and welcome you to first lesson of GD&T MasterClass series. But in this very first lesson, I'm not going to explain what is the GD&T or what are the benefits of GD&T. Instead of first understanding what is the GD&T, first I want you to understand how to learn the GD&T as a design engineer. Because as a design engineer, our main role is not to read and understand the GD&T drawings. Our main role, our primary job is to creating the GD&T drawings, which is completely different from reading and just understanding the GD&T drawings. So in this first lesson, we will learn what are the best process and practice of learning GD&T as a design engineer. And then what are the 3 core skills that we should focus on to master the GD&T as a design engineer. Because I have seen many design engineers, they know all the rules and controls of GD&T. They can also read and understand the GD&T drawings as well. But they are not able to create the GD&T drawings as per the standard. They are only using the GD&T control symbols, just an addition to traditional coordinating dimensioning method, which is not a good practice as a design engineer. As a design engineer, your drawings should be as per the international standard, whatever standard you choose, either ASME or ISO. So why do most design engineers not become confident when it's come to creating drawings in complete GD&T, even though they know all the controls and rules of GD&T? So you might say because GD&T is hard, there are so many controls and rules, and it's hard to memorize all the controls. So no, GD&T is actually easy. Yes, there is some controls and the rules, but most of controls are self-explanatory with their name itself, like positional control, parallelism, flatness, perpendicularity. Also, their symbols are self-explanatory. The main problem is the way we learn the GD&T, the way we think about GD&T. Because back then I was also struggling in creating the GD&T drawings as per the standard. Because all the books, all the courses I had studied, they taught me theory of GD&T. Like what is the GD&T, what are the rules of GD&T, what are the controls in GD&T, but no book taught me the practical of GD&T. Books and courses are like software tutorial. Software tutorial teaches how every tool works. For example, SolidWorks tutorials teach how extrude feature works, how revolve feature works, pattern works. But SolidWorks tutorials never teach how to design a particular machine or how to design a particular product. And this is same with the GD&T learning resources. They explain everything about the rules and the control or maybe simple use of it, but do not teach that how to create a GD&T drawings from completely scratch for a particular design with particular design intent. So how we can learn how to create a GD&T drawing of any part from completely scratch as per the design intent? And what does mean of this design intent? So for me, it's very simple. Creating a GD&T drawing of a part is very similar to designing the same part. And to be exact, it's more like redesigning the same part for the manufacturing. How? So let's understand it with an example. In this example, first we will understand that how we actually design a part step by step. And then we will create the GD&T drawing of the same part, and you will feel that creating a GD&T drawing is kind of redesigning the same part. And all the steps of creating GD&T drawings, like where to start, where to go, is very similar to the steps of designing the same part. And then what are the 3 core skills that we should focus on to master the GD&T as a design engineer? So let's say this is a 4-axis mini CNC machine. And in this G-axis, we have to design mounting plate for this motor. So what we should do as a first step, Well, we should visualize the overall shape of the part. And then we can evaluate the size of that shape, something like this. So we will mount this motor over this plate. And we will mount this plate over the existing vertical plate threaded holes. Also, the orientation of this part to be horizontal. So let's first try to design the overall shape of this part. So the first step is choosing the sketch plane. And you can choose any plane, but I will choose the top plane precisely. So create the sketch and extrude it. Now, the main reason of choosing top plate is because it's horizontal. So why did I choose the horizontal plane? Because this part is to be horizontal in assembly, as you can see, as well as also to be placed horizontally for machining on a milling machine bed. Because all the machinings, all the holes, all the drills to be done from top, and then also to be inspected in this same horizontal orientation over the inspection table, something like this. So what you will be call this information or message or whatever we are discussing right now, that how the part to be assembled, how the part to be manufactured or inspected. You guessed it right. It's a design intent. And this one is the first design intent of this part. That how the part to be set up, how the part to be rest, and the resting plane of the part for the manufacturing and the inspection, as well as in the assembly. And we define this setup intent with the datums like datum A, B, or C, which we will apply later in this video. And now back to the assembly. So now it's time to add all the features, all the holes, mounting holes for this motor and the mounting holes for this plate right here. So first let's try to fix this plate. It means mount this plate over this existing mounting threaded holes. So back to the part environment, or you can say the machining environment. These all are the machining tools like drilling and cutting and all those things. And I want you to feel the CAD software as your workshop. So first let's create the sketch over this top face, because all the machinings is going to be from the top during the manufacturing. So first here I am making the drilling points as per the measurement in the middle of the part width from this top edge as a reference, and then just drill the position. And this is the same as the machining process. Operator first take the reference of the holes from the side or middle of the part, and then they drill it. So let's place it into the assembly. And now we can mount this plate right here. And now we have to mount this motor over this plate. And this motor is with a guide step to precisely control the position of motor and with the 4 mounting holes. So which feature should we make first? This guide hole or these 4 mounting holes? So of course we should first guide this motor step into a hole with a slide fit or clearance fit to precisely control the position of motor. And then we can mount this motor using the 4 bolts with mounting holes. And I would like to maintain the motor step guide hole position with respect to these mounting holes, rather than from any side, top, bottom, or in the middle. So even if the overall size of the part will deviate, increase or decrease within the allowable tolerance limit, of course, this motor position will be remain same with respect to plate mounting holes, which is necessary as per the assembly. I will show you it's practical as well. And this is also a design intent, the positional design intent of this motor guide hole. Next, these 4 mounting holes of this motor. So I would like to control these 4 mounting holes with respect to motor guiding step hole. Neither from any side of the plate nor from these plate mounting holes. So when the position of this motor guiding step deviates within its allowable tolerance, the position of these 4 mounting holes will follow the position deviation of the motor steps guide hole. I hope you got my point. And this is also a design intent, the positional, or we can say locational design intent of these 4 mounting holes. So let's try to add these features as per its design intent. So create a sketch over the top again, and now take a construction line from middle of the mounting hole and make motor guide hole as per the nominal size at its nominal distance and cut it all. Take a sketch again, take the center rectangle tool and start from middle of the step guiding hole and set the nominal CD of the motor mounting and make all the threaded holes. That's it. Now bring back to assembly and make all the connection. And now if I will change the length or width of the plate, even if by 5 mm, everything will be remains at its place and will get assembled correctly as it's supposed to be. And now even if I change the position of mounting holes of this plate from the back side, everything will be remains in the place. And now if I will change the position of motor guiding hole with respect to these mounting plates, motor overall position will be deviate, of course, but the motor will be get assembled anyway, because the position of these all 4 mounting holes will be also deviate by the same. And this is the benefit of designing with design intent. And this is the main difference between designing a part or just CAD modeling a part. The main basis of designing any part is its design intent. And CAD modeling is just like creating 3D of any part. And we create the GD&T drawings to convey or communicate these design intent to the manufacturer and inspector. And if there is no design intent, then why we should make GD&T drawings? Just make simple drawings and just do the dimensioning from any side. It doesn't matter. So let's try to convert all the design intent into form of GD&T drawings. And in this part, all the design intent are mostly positional design intent. But the design intent can be also control the geometrical shape. For example, circularity control of this motor step hole. But for motor mounting, controlling the circularity of this guide hole is not required. We will see it later in this video. So we are here in drawing environment. And just for side note, I'm using third angle projection. So I will put top view at the top and bottom view at the bottom. And now first define the overall size, length, width and thickness, as we defined in the first step of the design. But here you can add the tolerance with the overall size. But in this case, general tolerance would be enough. So leave it as it is. Second, defined all the features locational dimensions as per the design intent. As we did it in designing. So I have defined the position of these 3 mounting holes of this plate from the top, from this top edge, and from middle, and the position of motor guiding step hole from plate mounting holes, and the position of these 4 mounting holes around the motor guiding step hole. Third, define all the feature size, but here you can add the fits and tolerance. So for this motor step, I have defined H7 because I suppose that motor step would be in G6. The fourth step is defining the primary datums. So how to select the primary datums, that we will learn in dedicated lessons. But here I simply want to say, we define the datums to communicate mainly 2 types of design intent. First is part setup intent, like how the part to be set up for the manufacturing or for the inspection, because first part to be properly set up. Second is defining the feature relations, like controlling the X feature with respect to Y feature. So we can define Y as a datum, and we can control the X features like its circularity or perpendicularity with respect to feature y. So always first try to define the main datum ABC to intent the part setup. So the manufacturer will knows that how part to be set up for the manufacturing or for the inspection, and then define the feature relation intent, like positional intent of the feature with respect to datum A, B, and C. But if you want to define a feature relation intent with a non-datum feature, like position of hole Y with respect to hole X, then define the X as a datum D, and then you can define the position of Y with respect to D. Datums can be whole also, or any feature of size. It doesn't have to be always a plane. And you can define as many datums as required. I hope you got the idea. So how we should set up our part? So as we discussed, this part is going to be rest horizontally first in machining or during the inspection process. So the bottom face is our datum A. And as we define the position of the first feature, these plate mounting holes, from the top side as a reference, so after resting the part at its bottom in inspection or manufacturing, we can constrain this face with a right angle as a setup intent. So define this datum as a B. And as all the features should be machined from center of the part width as a reference, means from the center plane between these two face width, means we have to constrain the width of this plate, not just the side of this plate. And to define this, we have to attach a notation of the datum B with the width size dimension. So this all datums A, B, and C are the part setup intent. And now let's try to define the feature related design intent. And as per my experience, it is always better to first define all the positional design intent, like position control, and then define orientations and geometrical form controls. So in coordinate tolerancing method, we used to control the feature size and also the location with the tolerance, something like this. So this indicates that this hole can deviate by plus minus 0.2 mm from this side, from datum B. But this tolerance cannot indicate that this hole can also deviate with respect to datum C, that how much this hole can deviate in widthwise from the center. Also, this tolerance cannot indicate that how much this hole can be tilted from its perfect axis, because the drilling is not going to be always perfect. But in GD&T, we can define everything with positional control. So here I have defined the position control, or you can say position tolerance, over this one hole with respect to datum A, B, and C. And in this case, I have to make this locational dimension under a bracket to make it basic dimensions, which indicates that this dimension values has no tolerance, as we controlling the tolerance from position control frame. And this position control indicates that this whole axis position, not the point, the axis is allowed to deviate within 0.2 mm diameter cylindrical zone. It's not a circular zone, it's a cylindrical zone. And this cylindrical zone is perpendicular over the datum A. And this is why we always include the resting datum in position control frame. And the axis of the cylindrical zone is at absolute distance from the datum B and exactly located on the datum C, which is in center of plane in this part. But if you haven't understood any control or datums in this video, please don't worry. We will discuss all these controls, all these rules one by one in dedicated lessons from completely zero as a child. in this lesson, I just want to show overall process of creating the GD&T drawings. I don't want you to focus on details. Just focus on the bigger picture, that how steps are taking, how the design intent is connected to the GD&T drawings. I just want you to observe the process. So as there are 3 holes and these are in patterns, so I have defined the pattern position tolerance. And I also add the material conditions also over the datum. We call it datum shift. But I want you to ignore this material condition and this pattern tolerance as of now. In this video, I want you to only understand that we have defined the position intent of this hole. So next is motor guiding step. And as per the design intent, this motor guiding step hole should be controlled with respect to mounting holes. These 3 mounting holes. So we have to define the whole pattern as a datum D. And now we can define the position of a guiding hole with respect to datum A, D and C, not respect to datum B. And as per the design intent, the position of these 4 motor mounting holes should be controlled with respect to motor guiding hole. So we can define this motor step as a datum E, and then we can define the position of these all 4 mounting holes as a pattern with respect to datum A, E and C. But as you can see, there are too many datums. So we can actually optimize it better. So instead of first defining the position of these mounting holes, define the position of motor step hole with respect to datum B. And then consider the motor step as a datum D. And with respect to datum D, defines the plate mounting holes, these 3 mounting holes. And as well as define these 4 motor mounting holes. That's the same thing. The result would be same. You can also download this from video description just for a reference. And now we can define the form controls. But in this plate, we don't need to control any geometrical form. Not even the circularity of this motor guiding step, which is a slide fit. Because the circularity, which is a geometrical form of this hole, can be deviate only within its MMC and LMC. Form of the part can deviate maximum at LMC. And if the part will be manufactured at MMC, then the form of the part has to be perfect, because this is the first rule of the GD&T. And in this case, even if part is at maximum deviation, means manufactured at LMC, this is completely fine, because the main purpose of this guiding hole is just to position the motor. So where we should actually apply the circularity control. So for example, let's say this is a bearing shaft. Now, in case of bearing mounting, we must ensure that bearing ID should be fully supported by the shaft for evenly distribution of the load. So the shaft OD, the mounting shaft OD, should be maintained under the tolerance zone, but should be also precisely circular in the shape. So the bearing ID and the mounting shaft OD will touch and support from all around. So here we have to must define the circularity control over the bearing mounting shaft. And we will discuss these kind of things in upcoming lessons in their dedicated videos. So we can say this drawing is final. Also, we don't have to define any flatness or anything. It's just the mounting plate. And if we are not defining the flatness, then it doesn't mean that this plate can be bent something like this. This plate can be bent within its LMC and MMC, and which is completely fine for this application. So as you have seen that 90% of time we talked about the design intent and how to convert the design intent in form of GD&T symbols. All the engineers and all the books says that GD&T save the cost and the time. And this is True, but I would say with GD&T, you can save the time and cost only if the designers knows all the design intent and they are correctly converting the design intent into form of GD&T. If they will apply GD&T just here and there, the cost will be increased, not decreased. GD&T is just a tool, but how you using it is the matter most. And our job is to use the GD&T correctly to creating the effective GD&T drawings. Effective GD&T drawings means, number one, drawings should be as per GD&T rules and GD&T international standard, either ESME or ISO. Number two, drawings should be clearly and effectively communicate all the design intent as per the assembly or the function of the part. Number third, drawings should allow maximum possible manufacturing tolerance, bonus tolerance, without compromising the functionality of the part to save the manufacturing and inspection cost. So how to create the effective drawings? And as per my experience as a machine design engineer, to create the effective GD&T drawings, we have to master 3 core skills. One is solid understanding of GD&T as per the standard. In this series, we will follow ASME Y14.5M-2018. A deeper understanding of GD&T rules and a standard, like 2 basic rules of the GD&T, Rule 1 and Rule 2, tolerance zone of each GD&T control, understanding of datum shift concept, making us more comfortable to allow extra bonus tolerance to reduce the manufacturing and inspection cost. Whereas the deeper understanding of own design, like what are the critical features of the part, what is the relation between 2 features, make us more confident and easier to choose that where we need to apply GD&T controls and where we don't have to apply any GD&T controls, because we must have to avoid the unnecessary GD&T controls which is not required as per the functionality of the part, because more GD&T control means more cost and time to manufacture and inspection. Also, the deeper understanding of own design intent make us more confident to choose between 2 GD&T controls, like between circularity and runout, or between flatness or parallelism. GD&T is just like playing a chess. If you want to play it properly, then you first must know that how every chess pieces works, all the rules of the game, but you have to also play it well, like when to play which chess pieces. How to play for the checkmate. You have to play with a strategy. You cannot play just randomly. Same in case of manufacturing drawings. The understanding the GD&T rules, all the controls is one thing. But where to apply, when to apply, which to apply is different thing. It all depends on your design, on your understanding of your own design. For example, as we have seen in this bearing shaft mounting example and this motor mounting example. So in short, we must have a solid basis behind every GD&T controls. We cannot apply GD&T controls without understanding of the design, without understanding of design intent. Because whatever controls and tolerance you define over the drawings is meant to maintain in manufacturing and then further inspected in physical. So now let's move to the third skill. Understanding of how the part to be manufactured and the inspect means the understanding of how the part to be set up, means we have to understand that how the part to be set up on manufacturing on the machining tools like milling machine or lathe machine or CNC machine. And a deeper understanding of these both things make us to choose the effective datums in GD&T drawings. Also, deeply understanding of manufacturing process tolerance allow you to apply optimum tolerance over the dimension, because how much tolerance we apply is depends on the design requirement, but also should be under the manufacturing capability and should be also possible to be inspected. Otherwise, part will be not manufactured, or if manufactured, the cost would be too much. But always remember, your design and drawings are based on your own thought process, your own feelings, ideas, experience, or the learning. It's just like a art. The more you will be feel it, the better you'll be become at your design and drawing. All the calculations, CAD modeling or GD&T that you makes are the reflection of your feelings, ideas and experience. And you are the artist. कैसे बोल लेता हूँ मैं ये सब? So what is the GD&T? Let's begin it from the zero. Video should be on your screen or you can check the description.